Okay, hello everyone. I'm Jack. This is Jasmine and Ethan. And for our research project over the summer, we decided to create a simulation for a chaotic 3D double pendulum. So what is a double pendulum? It is two pendulums connected together, end by end, and then they are dropped and they create very interesting visuals. They're notable because they have a very simple appearance. It's really just two connected lines that are then dropped. But they're very sensitive to initial conditions. As can be seen in the visual here, they're started at very similar positions, but very quickly the three pendulums will become distinct from one another. In this way, they easily demonstrate chaos. They are one of the easiest ways to demonstrate chaos. And despite them being fairly simple, they can actually vary in many different ways that greatly change their output. In this first simulation on the left, we put the bottom pendulum to have a lighter mass than the top pendulum. As you can see, it creates very chaotic behavior with the bottom pendulum wildly swinging around the top pendulum. For the second simulation, we kept the masses of both pendulums the same, but made the bottom pendulum shorter. This creates a little less chaotic behavior, but is still very different from if the pendulums were the same length. And then in this final simulation, we have the pendulum in 3D, which creates much more chaotic, much more interesting visuals. I'll now pass it on to Jasmine.
Hi, my name is Jasmine. So one of the first persons to study the double pendulum is Daniel Bernoulli. Now, he followed his family and became a physicist and a mathematician. Now, what he did is study the double pendulum, and he noticed that it had two motions, asymmetric motion and anti-symmetric motion. And with symmetric motions, the double pendulum, both pendulums would swing towards the same direction, but with this, he noticed that it had a low oscillation frequency, while anti-symmetric behaviors swung in different directions but had a higher oscillation frequency. So as you can see, there's like a little picture of the double pendulum. And if we saw it spin, which it doesn't because it's a picture, but if it spun, you would see that sometimes it doesn't spin that much, like the bottom part of the pendulum. That means both pendulums were swinging in the same direction. Meanwhile, sometimes it spun very chaotically and very fast for, I don't know why, but that would be anti-symmetric behavior. So why do we care? Well, the double swing, or the double pendulum, is actually prominent in the golf. When people swing in golf, there's actually a double pendulum there. As you can see by the stick figure diagram, there's darker lines which indicates the double pendulum. Now, the first link of the double pendulum would be between the golfer's shoulders, so like the chest area. This is where the golfer's arms and shoulders would rotate about. And the second link is where the golf club would rotate about. This would be the arms and wrists of the golfer. And as you can see in the first image, the golfer is getting ready to swing. He has his golf club up. And the second one and third one, he's releasing it and dropping the double pendulum. Now he's about to hit the ball. So now when you go see someone golfing, you can kind of confuse them and tell them that there's a double pendulum right there. So this is also going to be a photo because we downloaded them, but we can imagine, right? So these are 12 double pendulums. They're all the same, but their only difference is that they vary in different heights. So if you can imagine dropping these pendulums, a little variation in height. They drop, they swing. You would think that they would follow each other, maybe some go ahead, but realistically, if we saw it, they will all be spinning chaotically. We would have no idea which one's going where. Thank you.
Okay, so 2D pendulums are cool and all. They're very interesting. So why did we decide to make one in 3D? Well, for one, as you can imagine, they become much more chaotic in the third dimension. Having a whole new dimension for it to traverse in creates much more interesting visuals. Another is that it's very hard to find simulations for 3D pendulums. This visual here was one of the only ones I could find to simulate one. And it's not truly a 3D pendulum because the top pendulum only moves in the second dimension, so it's only the bottom pendulum that's actually moving in the third dimension. And the 2D pendulums, though, are very well documented. I mean, if you look up online, you can find hundreds of thousands of different simulations from like school projects to different, universities. So we thought it was interesting how 3D pendulums seem to be much less common. And the main reason for this, we found, was that they're very difficult to simulate.
So for this simulation, we had variables theta 1, theta 2, phi 1, and phi 2, and these represent the angular positions of these two pendulums. And then as you can see here, this is like a nice diagram to explain where the variables are and how we got them from. So in a 3D pendulum, you have to account for phi 1 and phi 2 instead of just theta 1 and theta 2. And then the derivatives represent the angular velocities, and then the second derivatives represent the angular accelerations. So the positions of the masses are defined using these functions and then with the lengths L1 and L2. So I'm just going to list off a couple of them. So x1 is equal to the length 1 times sine of theta 1 and cosine of phi 1. y1 is L1 times sine of theta 1 and sine of phi 1. And then z1 is negative L1 times cosine of theta 1. And then it's basically the same equations for the bottom part. But and then with these equations in mind, we created numerical functions with these variables. So explaining the simulation, the second part. So the kinetic energy for mass m, the kinetic energy T1 is equal to 1/2 m1 times v1x squared plus v1y squared plus v1z squared, where v1x, v1y, and v1z are the components for the velocity, this is the derivative. And then similarly for mass 2, it's similar. So I'm not going to read that out loud. So the total kinetic energy T is equal to T1 plus T2. And then the potential energy V is determined by its height above a reference point, and it's usually the lowest point of motion. And then for mass 1, the potential energy is m1 times g, where g is negative 9.8, and z1. And then it's similar for mass 2. And then the total potential energy is V equals V1 plus V2. The Lagrangian is the difference between the kinetic and potential energies, so L is equal to T minus V. And then for substituting the expressions for T and V, we get L as a function of the angles in the previous slide, theta 1, theta 2, phi 1, and phi 2, and their derivatives. Then we use a function from SciPy, which is a library from the programming language we used. We used ODE int, which stands for Ordinary Differential Equation Solver, and we used that to solve these system of ordinary differential equations. Just a side note, right now these are 4 second-order differential equations, but then they can be, the ODE int function right here, it doesn't accept second-order differential equations, so we had to split them up into 8 first-order ones. And then from there on, we just chose different initial conditions representing the velocities for the theta 1, theta 2, phi 1, phi 2, and then different positions. And then we integrated the equations over time to generate the trajectory. And then from that, we extracted the XYZ positions into a text file to simulate with a different library from Python. And then we used those positions to generate a 3D visualization of the double pendulum's motion. And then I'll hand it off to Jay.
Okay, so in this first simulation, we kept it pretty basic. We have trails for both ends of the pendulum. As you can see, the movement is very chaotic, very visually interesting as well. It's a little easier to see if you slow it down. So this is it with slower movement. You can more easily see both of the pendulums swinging around each other and creating chaos. And Here we have the same slow movement, but this time with longer trails. This makes it a lot easier to see just the path of both the pendulums and to fully visualize the chaos that they exhibit. And that is it for our summer presentation.